Welcome to this explainer. Have you ever stopped to think about the completely hidden digital infrastructure that powers, well, almost every single conversation we have? I mean, think back to those old, clunky, analog telephone wires. You know, the ones with the little plastic RJ11 clips that you practically had to wrestle into the wall? Yeah, those. Well, if you drop that right now and pick up a modern Ethernet cable, you are looking at a fundamentally different universe of technology. We've completely changed how human voices travel across the globe. So today, we're going to demystify exactly how that works and look at how the people who maintain it keep us all connected.
All right, here's our roadmap for today. First up, goodbye copper, hello VoIP. Next, we'll look at VoIP in everyday life. Then we'll tackle what happens when voice meets delay. After that, we're looking at the network's central brain. And finally, we'll wrap up with the technician's ultimate tool.
Okay, let's dive right into this. Section 1. Goodbye copper, hello VoIP.
The sheer scale of this technological shift is honestly massive. For decades, we relied on the PSTN, the Public Switched Telephone Network. This was your traditional dedicated copper network. It was incredibly expensive and honestly so heavy you could probably build a battleship out of the copper buried in a single city. Every single call essentially needed its own dedicated physical electrical path. But today, telecom networks have transitioned almost entirely to IP networks. We aren't sending analog electrical waves down a dedicated copper pipe anymore. Instead, we're sending voice as modern digital data packets.
So what exactly is VoIP? Well, Voice over IP is the technology that lets you make voice and video calls over a standard data network by converting your voice into digital IP data packets. Think about the gravity of that for a second. When you speak into a modern phone, your voice is digitized, it's chopped up into tiny little data packets, and it's sent across the exact same internet protocol network as everything else. Today, your voice travels across the world exactly like an email or a web page. It's literally just data on a standard network.
Moving right along. Section 2. VoIP in everyday life.
You actually support and use VoIP every single day, probably without even realizing it. I mean, it's completely ubiquitous. First off, we have over-the-top apps. Whenever you fire up a WhatsApp call, dial someone on FaceTime, or jump into a Zoom or Teams meeting, yep, you're using VoIP. Second, think about modern home phones. We aren't really plugging into those old wall jacks anymore, right? Fixed lines are now often plugged directly into the back of a fiber ONT modem. We usually refer to this as VoLTE or digital voice. And third, office IP phones. If you work in any sort of corporate environment, those desk phones don't use standard phone lines. They plug right into a network switch using a standard Ethernet cable. You are interacting with this tech constantly.
But why did telecom companies undergo the absolute monumental headache of ripping out all those old networks to make this shift? Well, the why really boils down to two major advantages. Number one is cost efficiency. Telecom providers realized, hey, we no longer need to build, power, and maintain two completely separate networks, one just for phone calls and another for the internet. By switching to VoIP, everything runs efficiently on one unified IP infrastructure. It's a real game changer. The second reason is advanced features. Operating on an IP network makes things like video calling, forwarding calls to your email, or hosting massive virtual meetings incredibly easy to deploy.
All right, let's look at the flip side. Section 3. When voice meets delay.
I want you to imagine a very specific scenario. A frustrated customer calls in and complains. My internet works perfectly. I can stream movies, I can download files, but my phone line keeps cutting out and sounding like a 1980s robot. So what exactly happens when voice meets network delay? You see, if you're downloading a huge file and the network slows down for just a single second, you're never going to notice. But voice traffic? Voice traffic is highly sensitive. It absolutely requires real-time perfection.
And when that real-time perfection breaks down, you're usually looking at an IP-level issue caused by three main culprits. First up, high latency. This is a severe delay in how fast those IP packets are traveling from the caller to the receiver. Second, we have jitter. This happens when there's an unstable arrival time. The packets are arriving completely out of rhythm, which makes the voice sound super choppy. And third, packet loss. This is exactly what it sounds like. Voice packets are getting completely lost in transit because of an overloaded router or maybe a bad physical link. The data simply vanishes before it ever reaches the other person's ear.
And this brilliantly illustrates a massive mindset shift. As a modern technician troubleshooting a phone line, you are no longer chasing an analog electrical circuit. You are fixing an IP application. VoIP turns voice purely into data And understanding that is absolutely crucial to diagnosing modern telecom issues.
Let's zoom out a bit. Section 4, the network's central brain. So how on earth do telecom operators watch over literally millions of these IP devices simultaneously? Well, they use an NMS, or a network management system. Now, this isn't just one single program. It's a collection of incredibly powerful software applications. I want you to picture this kind of cinematic environment, a massive network operations center, or a NOC. Imagine wall-to-wall screens, glowing maps of the globe, thousands of flashing green and red indicators. From this single central location, operators monitor, maintain, and configure the entire massive telecom network.
Because of this sheer scale, you really have to think of the NMS as the control room, or the central brain of the network. Without it, engineers and support teams would be completely blind to what's actually happening across thousands of cell towers, switches, and routers. The network is just way too vast, too complex, and frankly, too fast to manage manually. The NMS is basically the all-seeing eye that brings order to the digital chaos.
Which brings us to our final section, Section 5, the technician's ultimate tool.
Because the NMS software obviously can't physically drive out and look at a router, it relies entirely on IP addresses and specialized protocols, like SNMP, to act as its eyes and ears. It does this in 3 sequential ways, sending out these tiny radar-like pulses across the network. Step 1 is status tracking. The NMS constantly pings devices asking, "Hey, are you alive?" If a cell tower fails to reply, alarms trigger instantly. Step 2 is performance monitoring. It tracks the health of the devices over IP, measuring things like CPU usage, device temperature, and bandwidth limits. And step 3 is remote configuration. Instead of a technician driving 3 hours just to change a minor setting, engineers can use the NMS to securely update firmware or alter configurations completely remotely over the IP network.
So, why does this highly centralized software matter to the technician out working in the rain? Because the NMS dictates their entire reality. First, the NMS generates the specific troubleshooting tickets. When dispatch says Tower X is down, that alert came straight from the NMS. Second, and probably most importantly, it dictates when the job is actually done. A technician can splice a fiber cable or swap out a router all they want, but they cannot physically leave that site until the central NOC checks the NMS screen and verifies that the IP status has officially turned healthy and green.
So the crucial point is captured right here in what I kind of like to call the fundamental telecom paradox. Network management systems use the IP network to monitor the IP network. Just let that sink in for a second. It's a brilliant, self-referential system, but it also means that if a device somehow loses its basic IP connectivity, it simply vanishes. It disappears entirely from the dashboard, triggering a massive, critical alarm for the maintenance team to go hunt it down.
We've covered a massive journey today, from the death of analog copper wires to the birth of digitized VoIP packets, all the way up to the glowing dashboards of the network management systems. Remember this takeaway: understand your tools, master the IP path, and you will dominate the field. The invisible infrastructure is out there, quietly routing our voices and data at the actual speed of light. Now that you know how its brain operates, how will you use that knowledge the next time your voice meets delay? Keep questioning, and I'll see you in the next explainer.